For our project, Annika, Brandon, and I decided to model a sweat sensor to measure cortisol levels. Some background on abnormal cortisol levels and health conditions are that cortisol levels are usually measured through a blood test, and the normal range of cortisol levels in the blood is about 140 to 690 nanomoles per liter. However, this is a little bit different than the levels in sweat, but both sweat and blood utilize or follow the same pattern of depending on the time of day that the test is taken, which can be seen in figure one. You can see that there's a peak kind of in the morning of cortisol levels and it kind of decreases throughout the day. Cortisol levels can be used to characterize stress in certain diseases. For example, Cushing's syndrome is characterized by high levels of cortisol, and Addison's disease is characterized by low levels of cortisol and aldosterone. Therefore, a sweat sensor that can measure these cortisol levels in the sweat provides a non-invasive option to monitor these levels and potentially help diagnose certain health conditions such as Cushing's or Addison's disease, without the need to draw blood. Some goals that we have for our sweat sensor are to monitor cortisol levels through concentration of cortisol in the sweat. We also want our device to alert when the cortisol levels are higher or lower than average. To implement this idea, we used different color LEDs that will light up depending on the cortisol levels. A certain color will alert at high levels, which could help diagnose Cushing's disease, and a different color will alert at low levels to help diagnose Addison's disease. Both of these would be done non-invasively since we are using sweat. Some assumptions that we made for our model were that when converting concentration to current, we based it off of a logarithmic equation, which can be seen below. This equation was then linearized for the simplicity of our model and utilizes the units of nanoamps for current and nanograms per milliliter for cortisol. We also assumed that ideal components were used in the design of the circuit. And finally, we assumed that the device does not account for the morning spike in cortisol, and therefore the patient would have to be aware of the pattern of cortisol levels throughout the day, shown in figure one, in order to accurately interpret their results.
In order to achieve our goal of indicating to a user whether they have a high or low cortisol concentration, we use the circuit right here, utilizes a cortisol sensor on the left side, which outputs a current to a potentiostat right here, which converts the current to a voltage, which is processed by the comparators on the right side. And those comparators determine whether the LEDs will turn on signaling a high or low cortisol concentration in sweat. Going into further detail, the cortisol sensor that we decided to use is a wearable sensor, which uses molecularly imprinted polymer or MIP cortisol sensing, where cortisol in the sweat will react with the MIP layer and determine the current that is outputted. The electrode system consists of three electrodes, which are a carbon electrode, a carbon nanotube or CNT electrode, and a MIP electrode layer. And as you can see in the bottom right, there is a simplified model where a constant voltage of 5 volts is passed through the electrode and a current is outputted through the electrodes. And the current ranges from 906 nanoamps to 855 nanoamps for the normal, minimum, and maximum cortisol concentrations in sweat, respectively. Next, we have the potentiostat, which converts the current from the sensor into a voltage. And the voltage that is outputted can be amplified using this resistor T structure here. And based on the numbers that we chose for these resistors, we get a effective resistance of about 1 mega ohm. So this helps to amplify the small changes that occur from the sensor into a larger and more readable voltage output. And lastly, this capacitor at the top here helps to reduce any noise due to high frequencies from the sensor. Lastly, we have the comparators and LEDs, which compare the voltage from the potentiostat to reference voltages. There are two reference voltages for the high and low cortisol concentration, and they were determined around the normal cortisol concentration in humans throughout the day. When the voltage from the potentiostat is lower than the low reference voltage, the comparator will output a positive voltage to the LED, indicating a high cortisol concentration. And this is for the bottom comparator here. And on the other hand, for the top comparator, when the voltage from the potentiostat is higher than the high reference voltage, the comparator output will be a positive voltage to the top LED indicating a low cortisol concentration.
So here's our simulation. On the left, you can see with an input of 850 nanoamps, there is no LEDs. So 850 nanoamps would be about in between your high and low cortisol throughout the day. So most people would be seeing this no LED throughout most of the day. On the top right, you can see with an input of 800 nanoamps, the bottom LED turns on. So this shows a high cortisol. So this can be indicative of Cushing's disease if it occurs throughout the day. And then on the bottom right, there, with an input of 900 nanoamps, the top LED shows up. So that's indicative of a low cortisol, which could be associated with Addison's disease. Some limitation of our device is that sweat collection takes some time, so there may be some measurement delay. And although we can detect these high cortisols and low cortisols, real-time concentration has to be computed. Device users also have to be aware of the regular spike in cortisol when you wake up, because the red LED may show up, even though that could be a natural part of your cortisol cycle. And also, cortisol sensor, it has to be replaced regularly, which can become expensive if you're trying to measure your cortisol over many days. And some conclusions, our device design was successful because of the simulations. And our device has a better process of diagnosing these cortisol-related disorders because there's no need for a multi-day saliva or urine test. Our device focused on signal clarity, which we achieved, and some further work is that we could create and test our cortisol sensor on ourselves or in clinical trials, and we can explore using our cortisol sensor in addition to other biomarkers for expanded functionality. Thank you.